So this lecture, we're going to talk about stress. We've just spent a week or two talking about strain. These are very different things that we need to distinguish. So strain is deformation of rocks. And stress is what causes deformation. So why do rocks deform? They deform in response to stress. So stress is equal to force over area. So the basic idea is, force is important, but the area over which it's distributed is what really causes, what really matters in terms of deformation. And we're interested in studying stress in geology. There's some practical reasons as well as just trying to understand the deformation of faults and folds. Water behind a dam adds stress to the rocks and to the dam, and can cause a lot of problems if it's not carefully taken into account. And also in mining, it's very important as you're hollowing out caverns in the rock to have a very good understanding of the stresses that you're imposing on the remaining rock, or you can have some pretty serious problems. So the forces that are acting on rocks are basically gravitational and tectonic. And we can get a sense of the units and of the magnitudes of stress that rocks feel by looking at a simple case of stress in the gravitational field. So the question is, what is the force and stress acting on a 1 meter cube block at 10 kilometers depth? Due to the overlying column of rock. So we have this cube of rock of 1 meter by 1 meter by 1 meter, and it's buried under a lot of additional rock. That could be the surface. This would be 10 kilometers. So how much stress is that rock feeling? So we can address this question using this famous formula, Newton's second law. Force equals mass times acceleration. So acceleration is going to be the acceleration of gravity, or g. And we can get mass by multiplying density times volume. So typical crustal rocks have a density of about 2,700 kilograms per meter cubed. the volume of rock overlying the cube of rock that we're talking about is going to be 10 to the 4 meters cubed. So we get that from sort of 1 meter times 1 meter times 10 kilometers. 10 kilometers being 10,000 meters, 10 to the 4. So this will give us mass times gravity, 9.8 meters per second squared here on Earth. And this turns out to be about 2.7 times 10 to the 8th kilograms meter per second squared. So the meters cancel. We have kilogram meters per second squared, which is the same as newtons. That's the force. And remembering that force or stress is force per area. So the units for stress of Pascal, which is a Newton per meter squared. So this leads to the stress that this rock feels buried 10 kilometers down is 2.7 times 10 to the 8th pascals, or much easier to talk about megapascals, 270 megapascals. So just to get a sense of what a megapascal is, 1 megapascal is about 145 pounds per square inch. So you can imagine a sort of a ballerina up on her toe. It's about a 1-inch area, and she might weigh about 145 pounds. So 1 megapascal is about that much pressure. So this is the stress that this rock feels on a perfectly vertical face. So the next question then is, what about other orientations of faces? What stress is felt on a horizontal face or an inclined face? And to address that, we need more than just a single number to define the state of stress. We have something called the stress tensor. So a tensor describes the state of stress at a point. And tells you the information in all different directions. So it's a quantity that fully describes the state of stress on any plane with any orientation at a given point in time and space. So stress tensor has 9 components. So you might be wondering, what am I talking about? 9 components of stress. So one way to think about this is the difference between what we could call normal stress and shear stress. So a normal stress, let's see, let's start down here. Normal stress, which we're going to abbreviate with sigma, is a component acting perpendicular to a surface. And a shear stress tau is a component acting parallel to a surface. So we could think about this as basically, if I had a table surface here, and I could rest my hand on it, and I have some of the stress that this table surface feels is going to be the amount I'm pushing down on the surface. Another component is going to be how much stress there is that's going to cause sort of motion of my hand sliding on the table. So the downward stress is the normal stress, and that stress that wants things to slide is the shear stress. So that's just 2 components, but you can imagine, if we're talking about sort of one little point on that surface, one little point on that surface is also one little point on that surface and that surface and that surface. It's a 3-dimensional question of planes in all different orientations at that point. And this is just one of those planes. So you can imagine that you would need more than just those 2 numbers to describe the state of stress at that point. Fortunately, we can often simplify the situation to just talk about the normal and the shear stress. So for any stress state, there are 3 perpendicular planes, or 3 perpendicular planes exist where shear stress is 0. The normal stresses perpendicular to these planes are what we call the principal stresses. So the principal stresses are what we call sigma 1, which is greater than sigma 2, which is greater than sigma 3. So we can imagine that little point that is on that plane as a little tiny cube, and it's feeling on each surface of it some normal stress. We could just arbitrarily label those as sigma 1, 2, and 3 that we were just talking about. And each surface is going to feel shear stresses in both directions on that plane. And I'm not worrying about the sign conventions here. We're not going to get into it to that level of detail. But you can see, if you think of it like this, there's 9 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I had said before, if these are sigma 1, 2, and 3, then in this special case, all those shear stresses would be 0. So we could define the state of stress with just 3 numbers. So if sigma 1 is in sigma 1 through sigma 3 are all equal, we call that lithostatic stress. So this would basically be similar to hydrostatic pressure. So if you jump in a swimming pool, you're feeling sort of the pressure is equal in all directions. So this tends to cause sort of compression, so a bit of volume reduction, but it's not going to do it's not going to bend or break things. What does bend or break things is what we call differential stress, which is the difference between the largest and the smallest components of stress. This is what causes deformation. Most deformation. So the question is, what is the stress state on an arbitrary plane? So we can imagine a point in space, so feeling some normal stress, or sorry, some maximum stress and some minimum stress. So on the surfaces, as we'd said, perpendicular to the principal stress, the sigma 1, sigma 2, and sigma 3, that surface feels no shear stress, neither does that one. But at some orientation theta, there'll be some combination of normal stress and shear stress. So we could think about this plane experience, it's feeling sigma 1, right? But we could break that down into sigma and tau, normal stress and shear stress, and that angle also is going to be theta. So there are some nifty equations that describe the stress of a state on that surface in terms of the angles and the principal stresses. So the normal stress in that plane is sigma 1 plus sigma 3 divided by 2 is the average of the maximum minimum stresses. And then we have here sigma 1 minus sigma 3, which we call the differential stress, so half of the differential stress times the cosine of 2 theta. And shear stress equals, again, half the differential stress times the sine of 2 theta. So these equations this situation can be visualized with something called the Moore stress diagram. So the Moore stress diagram is a graphical way of plotting those equations. And we put on the x-axis normal stress and on the y-axis shear stress. And we can plot sigma 1 and sigma 3 are both at orientations where shear stress is 0, so they'll both plot on that axis. And we've defined sigma 1 as being the larger one, so that'll be sigma 1 and that'll be sigma 3. The average of the two there, sigma 1 plus sigma 3 over 2, will be in the middle. And these are the equations for a circle. And every orientation, every value of theta is going to be some point along the diameter of that circle. And we keep track of the orientation by defining this as 2 theta, that angle. So if we're talking about this point, it plots at 2 theta. So any value of theta, so if this was an angle of, I don't know, 40 degrees, that point would be indicated here by 40 times 2 by 80. So you go up to about there, would be the point, that the orientation that I've just shown there. So some things to note. For theta equals 90, so that would be that surface. That would be 2 theta equals 180. At that point, sigma, the normal stress, is equal to sigma 1. In other words, we're right there. And tau would be 0. There's no shear stress on that plane, as we said before. For theta is 45 degrees, 2 theta equals 90. So at 45 degrees, that would be 2 theta up here at 90, so that would be that right angle. That's when the shear stress is the highest it can be in any orientation. So tau equals tau max. And then finally for theta equals 2 theta equals 0, so that orientation, then sigma equals sigma 3. So normal stress that this plane feels is there, sigma 3. And tau, again, no shear stress at that orientation. So if this Moore circle business is a little confusing, the textbook is a good reference. Chapter 3, which was assigned for this week. And we'll also be working with the Moore circle in the lab. So to continue with it though a bit, we can sort of imagine some situations. So let's say that we're talking about a a surface with nothing on it. So there's no, basically the tape, the top, the counter and your kitchen counter with nothing on it. That would be a point basically there. There's a little bit of atmospheric pressure, but it's pretty much, geologically speaking, it's negligible. So we have zero normal stress, zero shear stress in all orientations. So let's say that we're talking about this point here on your table, and then let's say that we pile up a little bit of stuff on it. You can visualize that in the Mohr circle as doing that. So suddenly that point is feeling some force from above. So sigma 1 is, the weight of that is pushing down. And we can define that, so this would be our new little sigma 1 there. And if we were to continue adding more and more heavy stuff on top of this point, we would continue to move sigma 1 in this direction. So and if sigma 1 is in this direction, that means there has to be if we were to think about the other orientations other than that flat surface, they would be defined by the points along the diameter of that circle. And so I put even more stuff, another brick on top of there, or over here. So this would be the case of adding a load, but no confining pressure. So what does it mean that there's no confining pressure? Basically, that means if this stuff was viscous, if it could flow, then it's completely free to move in that direction if it wants to spread out. There's nothing holding it back. If we think of a rock that's buried at some depth, on the other hand, it is feeling confining pressure. If we think back to that cube of rock that was buried, 10 kilometers below the surface, it's feeling all this stress coming down from the overlying rock, but it's also feeling it can't just expand that way. There's other rock material there, so it is feeling confining pressure. So if it's lithostatic stress, when the stress in all three directions is equal, you'd plot on the Mohr diagram somewhere out here. So this would be sigma 1 equals sigma 2 equals sigma 3. So if all those stresses are equal, there's no plane is feeling any shear stress. But let's say that we were to reduce the confining pressure. So we were to sort of not push quite so hard on the sides of this box. Let's say that we were to sort of excavate some mining pits here. It's going to relax the confining pressure on this. And that's going to have the effect of reducing sigma 3. So let's say this is sigma 1. So sigma 1 is the stress due to this overlying column of rock. That's not changing. But as we excavate on the sides of this pillar, there's less and less force there to sort of support it on the sides. So sigma 1 doesn't change, but sigma 3 is getting smaller and smaller. And you can imagine if we were to just dig out all the way down on either side, so there's just a pillar of rock, basically we're back at this situation, right? There's nothing, there's just some air pressure basically holding up the sides, and we'd be all the way back to the origin. So this is the case of reducing confining pressure. So what's going to happen to this rock down here when we excavate around it? Eventually, it may well break, right? It may fracture. And it turns out that the Moore diagram kind of gives us a neat understanding or way of thinking about how the orientations of those fractures will be. So if we were to sort of plot that column as a cylinder, it turns out that those fractures tend to be, so let's say the cylinder is subjected to sigma 1 down its axis. These fractures tend to occur at about 30 degrees. Fractures, let's see, fractures at around 30 degrees to sigma 1. Oh, all sigma 1, yeah. Okay, so there's sigma 1, and that would be the angle theta. And where that plots on the Moore circle, if that's our Moore circle there, theta 30, 2 theta about 60. So those fractures tend to occur at a point on that part of the Moore circle. So at a point where the shear stress tau is fairly large. So that makes sense, basically. Fractures are places where, when if we push on this really hard, basically we're trying to shorten it, right? If you can imagine the situation of this pile of rocks, it wants to get shorter. And so sliding will occur in a very particular way on these surfaces. They're going to slide in a way that makes this column shorter. That's going to slide down, that's going to slide down. Now, if you very confining pressure, in a sequence of experiments, you find something like this. So basically, we're talking about taking several cylinders of rock, applying different combinations of sigma 1 and sigma 3 to them until they break. We can plot that on the Moore diagram. So this would be, let's do one experiment. So we start out, maybe we start out with sigma 1 and 3 equal, then we decrease sigma 3, and it breaks at a certain point. And we can plot that, what that Moore circle looks like at the moment that the fracture occurred. We can even measure the angle relative to sigma 1 that the fracture occurred at and mark it on there. And then we could do another experiment. Get a new cylinder of rock, maybe do it at a higher sigma 3. So let's say that this one broke at sigma 3 there. Let's do another experiment with sigma 3 is here. Increase sigma 1 until it breaks. Turns out it plots something like that. Bigger differential stress at a higher confining pressure. And then we do another one, even higher. Looks something like that. And if we plot those fractures, they tend to be at about that position. So we can define this surface here, basically that would go through these x's and intersect the circles. And that surface is what we call a fracture envelope. It's also known as the fracture criterion. And one of the things it's telling us is that as confining pressure increases, the shear stress on the fractures that form needs to get higher and higher in order for motion to occur, or for fracturing to occur. And one thing we can say about the orientation there, usually fractures are 25 to 35 degrees to sigma 1. Depends somewhat on rock type. It's never 45, which is a little bit puzzling. If you think about the Moore circle shows us that at theta equals 45, that would be, for any given Moore circle, maximum shear stress is at that point when that angle theta is, or 2 theta is 90 degrees. So it is the shear stress on those surfaces that's going to cause them to actually fracture. So you'd think maybe that when the shear stress was the largest, that's when the fracture would occur. But instead, it tends to be off to the side there. And so basically, the way we can understand that is this point has, just because of the shape of the circle, basically, both of those have a very similar shear stress. But there's a significant reduction in normal stress from that point to that point. So it turns out that you can imagine, as one of the things that the Moore circle is telling us, if you're going to try to have break a fracture on some surface, it's easiest to do it when you're not pushing very hard together, when the normal stress is pretty small. So we can basically apply almost the same shear stress in the situation if we're over here, but significantly decrease the normal stress. So that's why these fractures are occurring sort of not at the maximum shear stress, but still pretty high. And this plot in this surface here, the fracture envelope, gives us a way of predicting when rocks are going to fail. So if we're digging, one of the exercises in the lab on Friday will be to basically to predict, the size of a pillar that would be needed in a mine in order to hold up the roof of the mine without having that pillar actually fracture. So this surface tells us that. So if we were like, okay, the overburden is, the weight pushing down is over here, what's the area of that, what's that would keep that circle safely, away from the point where you're going to have fracture. And we'll talk more about that, and we can go over questions on this lecture in the lab on Friday.